Is that changing? Okay,
All right, I'll go ahead and share my screen.
excellent. So the next talk is by Colin Ophus. Some people think possibly he's still in Lawrence Berkeley lab, but now he is in professor in Stanford. So go ahead, it's all yours.
All right, well, thank you guys so much for inviting me to give this talk. So I saw that Gerd and others were covering a lot of nanobeam diffraction, and so I've slightly changed my topic today. In the original abstract, it was listed as 4D STEM, and so I'm going to give a fair bit of information about 4D STEM, especially ptychographic imaging and other similar phase contrast imaging methods, but I'm also going to cover tomography as well, because we have a large machine learning effort in that direction too. So, as Garrett mentioned, I am now at Stanford University. I moved there about a year and a half ago. And so I run a group that's focused on computational analysis and design of scanning transmission electron microscopy experiments primarily here. So in today's talk, what I want to cover is a brief introduction to scanning transmission electron microscopy and the four-dimensional variant 4D STEM. Then I'm going to give an introduction to tomography, especially atomic resolution tomography, what we call atomic electron tomography, or AET. And then I'm going to introduce phase contrast scanning transmission electron microscopy, and specifically so that I can introduce ptychography, which is the best of the phase contrast imaging methods, and ptychographic atomic electron tomography. And so that's going to be the limit of the classic stuff that I'm going to be discussing in today's talk. And then I'm going to move on to machine learning augmentation for 3D imaging and electron microscopy, specifically using our implicit neural representation architecture. And then I'll jump into using neural priors for ptychographic imaging here to make our reconstructions more robust, more accurate, and faster as well. And so for both topic 4 and 5, I've also prepared a Google Colab online tutorial. And if there is time, I will briefly flip through the slides, but I will give a link to everybody in the audience so that if you want to work through the code yourself, you're able to do so. Okay, so starting with scanning this as a characterization technique is because it is so flexible and powerful. You can do imaging by scanning your probe across the surface and using single pixel or segment detectors. You could add an aberration corrector, so you can push your probe size down to atomic resolution. But as Garrett showed in the previous section, you can also work with diffraction patterns. So in the far field here, if we have a pixelated detector, we can measure our diffracted stem probe here. Now, of course, we can also do spectroscopic imaging or spectroscopic scans of our sample using, for example, X-rays or emitted light from the sample. That would be X-ray energy dispersive spectrometry, XEDS, or CL for cathodoluminescence, or PL for photoluminescence. Or in the forward direction, pass the electron beam through a spectrometer, separate it out into different energy losses, and measure all sorts of different sample parameters and structures and bonding structures here. And then combine each of these methods with tilting of the specimen stage for three-dimensional tomographic imaging. So it is an incredibly flexible tool. That's why we call it a synchrotron in a microscope. So if I were to go and look at the imaging in detail here, we start with a converged electron probe focused on a sample. We scan over the sample surface, and classic STEM imaging, we use a single pixel annular dark field detector or similar detector to measure a single pixel value at every probe position. But what this would do is it would leave behind the rich signals in the diffraction pattern. These days, we have these pixelated direct electron detectors. They are fast enough that we're able to record a full picture of the diffraction pattern, take a step, record a full picture, take a step, record a full picture, take a step. And so this is what gives this family of techniques its name. 4D STEM stands for four-dimensional STEM because we're recording two-dimensional images over a 2D grid of probe positions. So this is a huge amount of data, a staggering amount. Here, in one of my first experiments on 4D STEM, we're averaging 40 by 40 probe positions. And you can see diffraction patterns corresponding to vacuum or single layer of tungsten disulfide or double layer. But here, it's not representative of the size of the data. If I average 7 by 7 probe positions, this is a little closer. but it still doesn't give you a feel for the millions of images that we're able to record here. This is an old experiment recorded in 2018. We had 256 by 256 probe positions and almost 2000 by 2000 pixels for each image. So over 400 gigabytes recorded in 3 minutes. Now our detectors operate over 100,000 frames a second, and we can get 1 terabyte of data every 6 seconds here. And so this is why we need robust software analysis methods to be able to process all of this data here. And this is where machine learning can really help us out. So why would we collect all of this information? Well, here's an example on a couple layers of boron nitride. And this is that conventional single pixel image that I showed you before, annular dark field, and the Fourier transform embedded in the upper right. And here we use the ion microscope, helium ion, to make single nitrogen vacancies, but it's impossible to see where they are. The sample signal to noise is far too low and the resolution is poor. But the technique I'm going to talk about today, ptychography, exactly the same electron dose, the same sample region, but using all that 4-dimensional data, we can computationally reconstruct our object. And now at this high resolution and high signal to noise, we're able to see those single nitrogen vacancies at the surface and that larger triangular defect. So about a factor of 4 to 5 increase in spatial resolution, but a lot more importantly, a factor of about 20 improvement in signal to noise. On the opposite end of the length scales here, we can also focus our electron beam down and record a nanobeam electron diffraction pattern, but our step size between adjacent probe positions is as large as we want it to be. So we can decouple field of view from resolution. The resolution comes from the interaction volume of the probe with the sample, but the field of view is such that in this synthetic example I'm showing, you could scan an entire 10 micrometer field of view of a battery sample from the cathode to the anode, and including both current collectors on both sides here. And then once you have that large data set of diffraction patterns, you could do virtual imaging, measure crystallinity, strain, classify structures, crystal orientation, or even more exotic channels here. So today, I'm actually not going to talk about a lot of the 4D STEM nanobeam processing, partly because we previously used a lot of classic image processing, and currently we're working on several machine learning versions of these codes, and they should be ready for release by about this time next year for the next summer school. So something to look forward to next year. So to summarize here, if you do 4D STEM, you can improve resolution and signal to noise, especially in imaging. And in nanobeam mode, you can measure structure over the functional length scale of the material, whatever it happens to be. Okay, so now a quick background on tomography. One of the huge strengths of the electron microscope is its high spatial resolution. So if you scan, for example, this nanoparticle, iron platinum, at atomic resolution, you can repeat this at many, many different tilt angles here. And so if we do tilts about every 2 degrees and use computational imaging, we're able to reconstruct it, in this case using a back projection algorithm called GenFire, and recover the 3-dimensional structure. So here is an isosurface that I've created, or 2 isosurfaces, I should say, in my 3D volume. And I'll just pause it briefly to show you what I've drawn is a low-level isosurface in red that really highlights the iron atoms, and then a much brighter isosurface in blue that shows you where the platinum atoms are. And that's because platinum scatters much more strongly than iron. And so from this reconstructed 3D volume, we're able to trace out all of the atoms and get atomic coordinates. And so here I've drawn all the grain boundaries inside the material for the different chemical regions of iron platinum for this L12, L10, and A1 structure. And so I just wanted to quickly point out too, if you project along the Cartesian directions, the 100, 010, 001, and then you color it based on the local ordering, whether it's L12 or L10 ordering, you actually get the complete wrong answer. And the reason is in 3 dimensions, the grains are much more complex here. It's essentially 2 C-shaped grains wrapped around each other. And so this is just showing the need for 3-dimensional imaging if you want to understand your sample here. Okay, so that's the background on tomography that you'll need for the machine learning sections that we're going to discuss in a bit here. So now, background on phase contrast imaging and ptychography. So why do we do phase contrast imaging? Well, in this previous iron platinum example here, the sample can tolerate a massive electron dose, hundreds of thousands or even millions of electrons per angstrom squared. And even iron is at least intermediate on the periodic table, intermediate atomic number, so it scatters reasonably strongly. But this imaging mode produces no contrast for carbon, oxygen, lithium, nitrogen, or other important low atomic number elements. If you contrast this to phase contrast imaging, this is the plane wave imaging mode in TEM. I love this image that I reconstructed in about 2016 because every white dot represents a single carbon atom. So here we were studying graphene grain boundaries, these high angle, close to 30-degree angle boundaries, looking at the reconstructions, the 5-7 member rings. And it was easy to do because we have every single atom visible. So in converged probe mode, STEM, how would we measure phase contrast? Well, the simplest method is differential phase contrast, and the atoms themselves have a coulombic or electrostatic potential because the orbitals of the electrons are displaced away from the positive ionic core. And so this inbuilt electric field causes the beam to shift its momentum vector as it passes over or nearby. So for example, with a segmented detector, shown in this Shibata paper here, you can measure the presence of an atom by seeing the beam is steered uphill, up the potential gradient direction. And of course, you can measure the same thing from electric fields or magnetic fields. Very useful because this is how we build our transmission electron microscope, but I'm not really going to talk about that here today. So just to show you what DPC looks like very briefly, when I scan in over a step function here, you get a slight momentum change of the probe. It's a lot easier to see if I bump up the step size here. And you can see also that the change in potential, the gradient of the electric field, or meaning the electric field, it will scale linearly with the momentum shift that we expect. And so we could, for example, use a segmented 4-pixel detector to measure the center of mass shift of these probes here, and then thereby reconstruct the sample potential. So just to show you what that looks like, here's a toy model in nanobeam mode, where I'm scanning through a nanoparticle with a bunch of atomic planes. The middle panel shows you what we measure on the detector. Those are our diffracted Bragg spots, but we're not able to pick up the atomic contrast because it's just a phase shift of the beam, right? So if you look at the bottom panel, as I scan through, you can see the colors flickering up and down as the phase of the diffracted beams change, but quantum mechanics says we can only measure the amplitude squared of the probe. So what you get out of this is a center of mass shift, the green line of the probe, and you can numerically invert it by doing Fourier integration, and you can reconstruct the shape of the particle, but not the atomic planes. So we get atomic spatial resolution by increasing the convergence semi-angle. And now what happens as I scan through the sample, these diffracted beams overlap each other. And so we alternate between constructive and destructive interference as we scan through the atomic planes. And thereby, from that center of mass, we can numerically Fourier integrate it and recover some of the atomic lattice here. Now, of course, it's damped because not all of the sections of our detector are participating in the constructive and destructive interference. So if I boost it to a super high convergence angle here, now the probe is much, much sharper than the atomic columns. The center of mass completely maps out the shift in momentum vectors. And if we reconstruct it, we recover the true sample structure here. So there's no free lunch, though. This is infinite signal to noise. If I drop down to 500 electrons per angstrom squared, you can see I get a much, much noisier reconstruction. And if I flip back and forth between the 2 millirad, 6 millirad, 32 millirad, you can see there's this fundamental trade-off between the reconstructed resolution, the features that we're able to resolve, and the signal to noise. So very, very large convergence semi-angle, high resolution, but low signal to noise and thereby low precision in the reconstructed phase. And then the 6 millirads sort of in between, and the 2 millirads, we're not able to resolve the atomic features, but we have very high signal to noise here. So this is what the 4-pixel differential phase contrast can buy you. What can you do if you do 40 STEM? Well, if we look at the atomic details in the far field here, these are 4 synthetic examples of tungsten disulfide here, showing that the diffraction pattern has this rich shadow image of the atomic lattice. And as I go to the lower right, I move the crossover further and further away. you can see that we're getting more unit cells of our tungsten disulfide hexagonal lattice in the field of view. So essentially, what we're going to be doing here is we're going to be taking a measurement and then another measurement and then another measurement, and in the overlapping information of our sample between adjacent probes contains enough information to calculate the phase, so the complex reconstructed wave function of both the probe and the object here. And it's very important that you have this redundant information. For example, if I made a measurement here, and then I made a measurement here, and then I made a measurement here, right? I have no overlap between the adjacent diffraction patterns and therefore no redundant information. So if you're trying to do ptychography yourself on the microscope, you want to aim for somewhere around 80 to 90% overlap of adjacent probes. So the algorithm itself that I'm going to discuss doesn't matter too much. It's basically just gradient descent. We're simply running the scattering equation in the forward and backward direction here. And I want to skip the details here to get to the machine learning augmentation of this, because it's a lot more interesting, I think. But I will briefly show you schematically what it looks like. We start with a guess of the probe, and then we start with a guess of the object. And the object is initially empty. We're saying no phase shift in the object, meaning it's just a t=1 transmission grading. And if you multiply the probe by 1, you get back that same probe. So we figured out by calibrating the microscope, each of these red dots is one of our measurements. So these are probe positions in the object field of view. And so if we take that probe and we multiply it by one of those probe positions, the t=1 transmission grading, in the far field, you get a diffraction pattern of just the unscattered central beam, that 0 spot, right? Now, if you compare that to the experiment has this hexagonal diffraction. This is the data set from the Cornell paper in the lower right, that Nature paper from Yi Jiang. So to reconstruct this tychographically with gradient descent, all you need to do is take the difference between the experimental diffraction pattern and the current model diffraction pattern, and then do back projection or back propagation. So we use the adjoint operator of the forward scattering, and then we update both the probe and the object. And this can be done iteratively. Now we can again simulate in the forward direction, take the difference, back project, simulate in the forward direction, take the difference, back project, and we repeat this until we have a converged guess of the probe and the object wave functions. So as a quick summary of stem phase contrast here, this is comparing all the different imaging methods that we can use. So the dark field image is that single pixel detector I mentioned. For a highly defocused probe on this gold nanoparticle, you simply see a big blob. If you switch to doing differential phase contrast here, you can get a much higher signal to noise, but it's still effectively a big blob because we're not adequately solving for the aberrations and then deconvolving them from our sample. There's an intermediate method that my group tends to call parallax, also known as tilt-corrected bright field. You treat all of your measurements as plane waves and try to reconstruct the sample. And then from that, you're able to get a much higher resolution image of the sample because you're essentially able to deconvolve the aberrations. But nevertheless, it does not hold a candle to ptychography, especially if you fully converge ptychography. And this is because the ptychographic reconstruction algorithms are essentially solving for the probe and deconvolving it from the object. And so if you're able to do that successfully, you get the highest resolution and the highest signal to noise possible here. Okay, so now combining the two sections I showed you before to give you an idea for the state of the art in electron microscopy, this is a zirconium tellurium nanowire encapsulated in a double wall carbon nanotube. So if I were to look at the different imaging modes here, the HADAF, the high angle annular dark field, I see the zirconium, I see the tellurium, but no nanotube. If you look at the middle panel, differential phase contrast, now I can see the double wall carbon nanotube, but the resolution suffers, especially in the nanowire. Only ptychography is able to get the atomic resolution details in the nanowire and the nanotube, the double wall carbon nanotube. And so having selected ptychography, we scan and reconstruct the probe, and then we repeat over many different tilt angles. And so what this gives us is a very wide range of projected structures in 2D. Here are some class averages, and this is the reconstructed 3D volume. And you can see that we are able to recover every atomic site here, right? And so in most of the carbon nanotube and all of the zirconium tellurium nanowire, we can use the integrated intensity to say, is this a zirconium atom, a tellurium atom, or a carbon atom? And the structure ended up being fairly complex here. This is a cross-section view showing the shell structure, which is the ZRTE5 units arranged in this sort of 90-degree arc. And then the core structure is ZRTE2, a new allotrope of ZRTE, but you could make ZRTE2, the structure that we found, by peeling off the outermost two tellurium atoms. And we also found isolated tellurium chains at the top and bottom of this structure. And tellurium is known to be able to solve or to form these one-dimensional chains. Okay, so that's the sort of summary of everything that I wanted to show you experimentally for the state of the art. And I wanted to ask a couple questions. For STEM technique development, are we done? Is ptychographic atomic electron tomography the ultimate method? Well, we're nowhere near finished technique development. And I do think PATE is the sort of ultimate method, but there's a lot of work we can do on the computational side to dramatically improve the reconstruction qualities. And that's what I'm going to show you here today. So discussing the limitations here, these tomographic tilt experiments, they take very, very long times. If you can record a single image and tilt and focus your sample in a minute, and then you need to record 100 images over many different tilts or 200 images, you can spend hours just looking at a single sample on the microscope. And of course, alignment in the electron microscope is quite poor at atomic resolution. The stage has hysteresis, it has some jitter. The samples themselves can also rotate too under the action of the beam. And speaking of the action of the beam damage is always a huge enemy here. Every time you image something with the electron microscope, you are causing damage to your sample. It's just a matter of how quickly it happens. And so in particular for tomography or ptychography here, it's very, very important that your assumptions in your algorithm, if you're assuming the object stays the same, that you don't cause damage to it during the tilt series or during the scanning series for ptychography. And then finally, when you do the reconstructions I showed you previously, there are so many user set hyperparameters. In both tomography and ptychography, you have to set everything from gradient update steps to regularization parameters, alignment parameters, how quickly you converge, how quickly you shift. There are just so many values here that you have to set as the user. So what I want to spend the rest of the talk discussing is how we're trying to get over these limitations for tomography and ptychography using machine learning here. So this is the basic framework that every group, except for my group, or a few other groups, use for directly using PyTorch with, say, auto differentiation to update our current gradient descent physics models. So I think the first paper that covered this was Wouter van der Broek and Christoph Koch in PRL way back in 2012, when they pointed out that inverse multi-slice or inverse multi-slice ptychography essentially was a neural network that we were solving, right? So the basic idea is we have a representation of our object, and then we have our microscope parameters. So think in ptychography, the probe positions, the angle of the diffraction patterns, the defocus or spherical aberration or astigmatism of the probe, etc. And then we use that model of the object and the microscope parameters, feed them into a physics model, predict the intensities, and then take a loss function of the difference between our prediction and our experimentally measured data. And then we backpropagate that loss to update both the object and the parameters here. And so auto differentiation, you are learning your object, your probe, pixel by pixel, or for 3D tomography, voxel by voxel, right? And this model is quite successful because your parameters, if they can be differentiated, you can solve these nuisance parameters. So if you think you tilted 2 degrees, but your stage actually tilted 2.1 degrees, you're able to refine and solve that difference of the tilt. So this is not what my group tends to do, though. We use a different model from the machine learning literature. We use a generative machine learning approach. So the idea is to select a deep prior of some type and then use it to generate your object or your object in the probe, rather than directly learning on the pixels or the voxels. So you can see the model is very similar. We have the same object and parameters representation, the same physics model, the same predictions. So we're still doing physics in the loop AI, but when we backpropagate our loss, that's not fed into the object and the probe, it's fed into this deep prior. And so this one that I've drawn here, this sketch, is called a deep image prior typically in the literature. And the idea is you have random noise, you pass it into something like a UNet, a CNN, convolutional neural network, and then what you're learning is the weights, which are then going to modify that noise and update your object. However, as you're going to see in a moment here, I'll probably discuss, we actually find that for physics experiments, you can't put random noise into your deep image prior. Instead, you need some sort of a correlated signal. And I think this is just because our measurements are a lot more correlated than the incoherent visual light imaging that most of the machine learning community uses. So what we're going to do, though, is we're just going to use the top loop, right, the original backpropagation auto differentiation loop, run it for 10 iterations. That gives us a prediction for the object, and that's what we call pre-trained object. That's passed into the deep prior, and then we simply learn the weights to fine-tune what that object should look like. Okay, so what does this look like in practice? Well, let's look at our tomographic example first here. So in tomography, the main artifacts are missing wedge artifacts. So what do I mean by that? Well, what I'm showing is a range of tilt angles, and then in the one column over, the reconstructed slice, and then the Fourier transform on the right. And so what you can see is that as we remove slices, right, from our reconstruction, in Fourier space, this manifests as this missing cone of information called the missing wedge artifact. And if we have a small missing wedge, you can still see atomic details. But as soon as the missing wedge passes a critical size here, you can see I have my vertical planes of atoms, but my horizontal planes have disappeared, and I have smeared out my atoms, and I can't trace their coordinates. So you can see a similar thing, what's called the small missing wedge artifact, if you undersample the angles. So instead of collecting every degree, if I do every 2 degrees or every 4 degrees or every 8 degrees here, you can see our reconstruction quality significantly degrades. So again, pausing this movie, right? Here, I get all the atomic details. If I remove every other plane, I get some streaking, but it still looks relatively good. However, if I go really far and I remove a lot of atomic planes, all the sites are going to smear into each other here. Okay, so what does our framework look like when we're applying this to electron tomography? Well, here we're going to use an implicit neural representation as our deep prior. However, everything else is kept the same as our previous algorithm, our auto differentiation algorithm. So what that looks like, an INR, you may be familiar in the literature with the terms neural radiance field or Gaussian splatting. They are very closely related to this. They are all different types of implicit neural representations. So what is an INR, or an implicit neural representation? If you think about an image, you have this x comma y coordinate system, and you have 1 pixel for every x and y unique value, but you also have a minimum x and a maximum x and a minimum y and a maximum y. Same thing in tomography, right? You have 3 coordinates, x, y, and z, but that's your whole field of view, and you have to index individual voxels. What an INR does is you replace this by using some kind of machine learning network where you simply pass in the raw coordinates, the x, y, and z coordinate, and then it predicts the intensity. So this has no bounding box. It has no discretization, right? You simply ask it what the given intensity is at a given coordinate, and you get back a prediction. And so for our initial implementations here, we used what are called MLPs, multi-layer perceptrons, depth 3 or 4, and then just applied directly this implicit representation from R to intensity. So to adapt this to tomography, all you need to do is sample along different rays, right? Because our projected image in ADF tomography, ADF STEM, we are assuming you're taking the sample reconstructed volume, whatever it is, you add it up voxel by voxel, and then when you reach the end of the object, that's the predicted intensity of that pixel. So the entire reconstruction loop looks something like this. We're doing pixel by pixel loss, where we're back propagating the difference between the integrated intensity and then using that to update the weights of our INR and to update the poses or the tilt and shift of our individual images here. So the INR has a whole bunch of advantages. The first up is you don't have to specify a minimum and a maximum position ahead of time. It is a continuous representation. And speaking of it being continuous, this is beautiful when you want to do things like regularization, because normally, let's say you do total variational regularization, you have to look at the difference of pixels against their neighbors or voxels against their neighbors. However, here we can do exact regularization because we can differentiate the network on a continuous field. So we can always evaluate any operator with arbitrarily high precision on the network. And then the last thing, which is a little more subtle, this loss is pixel by pixel in the output images. So this is the most parallelizable algorithm I've ever seen. If you have 50 different tilt angles and you have 1,000 pixels in every image, in theory, if you had 50,000 GPUs, you could parallelize it over 50,000 GPUs because you can do each individual pixel one at a time, right, as a parallel sort of atomic unit. Okay, so why do we do this? Well, implicit neural representations and other machine learning in-painting methods are so superior to classical methods for in-painting missing information. So what I'm showing here is this phantom along the top row, and then the middle row is our INR reconstruction, slices showing the missing wedge in the vertical direction, and then below it, SIRT, or simultaneous iterative reconstruction technique tomography. This is just an iterative gradient descent tomographic reconstruction based on the radon transform. And so if you tilt from -80 to +80 degrees in the lower left, a 20-degree missing wedge, SIRT gives you a great reconstruction, so does INR. But as you move left to right and you drop out more and more angles, ending up with a tilt range of only -20 to +20 degrees, the classic algorithm smears out the objects and gives you essentially nonsense. But the INR, even with a tilt range of only -20 to 20 degrees, is still able to accurately reconstruct the objects inside. Now, it's not perfect. Our phantom contains this thin membrane on the outside edge, and you can see even by a missing wedge of 80 degrees, you're already starting to lose some of your membrane there, right? And then by the time you get to a missing wedge of 140 degrees, we're barely reconstructing that outer membrane at all. So it is somewhat feature dependent, but nevertheless, the INR does a much, much better job of in-painting the missing information. So similarly, if you just remove different tilts, so you go from 180 images down to 36 images, to 16 images, to 9 images, to 5 images, you can see the degradation of the classic algorithm. Even 16 images, it's already essentially just streaks, right? But the INR is able to almost perfectly reconstruct the objects. And even 9 different tilts is enough to reconstruct most of the membrane and all of the objects inside. Now, of course, the INR is not perfect. If you have only 5 tilt angles, it is not able to recover an accurate structure. But think about what this means on the microscope, right? If you reconstruct from 9 images instead of 180 images, you've saved yourself a factor of 20 time on the microscope. And these algorithms can be run during data collection. And so you can collect more and more tilts or more time points or more scan points for your experiment on the microscope until your error tolerance using cross-validation drops below a given set value. And so these are very, very powerful methods to dramatically improve the reconstruction, but also speed it up to the experiments. So here's what it looks like on actual experimental data. This is just showing on the left the INR and on the right the conventional reconstruction. And I just want to highlight a couple things here. More details in a moment. Essentially, what I want to show you is the streaks on the right-hand side. These are alignment errors. The stage is only accurate to about 1 degree when you tilt back and forth due to hysteresis. And that small angular misalignment completely destroys the high resolution details of your sample. But as long as you're doing a joint reconstruction and auto-differentiating over nuisance parameters like the mistilt here, you can solve those orientations to arbitrarily high precision. So here are 3 slices taken from those 2 reconstructions. And in the interest of time, I'm just going to focus on these 2 slices. So left is the INR, right is the tomography, and it's like night and day. The large missing wedge, almost 90 degrees, gives you these streaks from the catalytic gold ruthenium nanoparticles. And so you get these weird artifacts where you have like extra ghost nanoparticles appearing, and then a hole in the middle of the sample, in the shadowed region of the missing wedge. And similarly, you also get ghost intensity out in the vacuum. Now, the INR reconstruction, initially, we were wondering why there were 3 different levels, right? You can see the high brightness gold ruthenium, the intermediate brightness for titanium oxide, the known support, but these dimmer blue regions. And so I ascribed these to amorphous carbon, And the students, of course, insisted that the sample was clean, but I made them do some quick X-ray chemistry, and lo and behold, there's significant carbon contamination in these samples. And so the INR is able to very accurately reconstruct all of the sort of constant volume intensity regions of the sample. So the ground truth is known in the synthetic phantom. Of course, we don't know the ground truth of the experiment, but we can still test the INR performance by deliberately removing information. So the experiment went from -70 to +70 degrees. And so we're able to determine that if you then drop all of the tilts outside of -40 to 40 degrees, you get essentially the same reconstruction. However, if you go down to 20 to 20 or 10 to 10, then the reconstruction quality significantly degrades. Same thing for number of projections. After the fact, we definitely learned we did not need 71 projections using the INR. We can get away with 15 or maybe even 11 projections. However, if you drop down to 6 or 3 projections, then the quality is too low to make the measurements that we want to on the sample morphology. And then finally, signal to noise. If you run these machine learning networks, they are astoundingly good at denoising. And so if we estimated our initial fluence of the electron dose was about 10 to the 4 electrons per pixel, and then we drop it by an order of magnitude or 2 orders of magnitude, we essentially get the same reconstruction. It's not till we drop to 10 or even 1 electron per angstrom squared that we start to see significant degradation of the resolution. Okay, so I will leave this till the end of my block to see if I have enough time, but I did want to throw this up here as a tutorial. So if you guys are interested in this machine learning approach to tomography, please follow this link. This is Google Colab tutorial, and it includes the phantom data. And I believe this tutorial does a classic CERT reconstruction and then our INR reconstruction on the same volume. And so if there's time at the end, I will flip through these slides with you and quickly explain how this tutorial works. Okay, so last bit on tomography here. This is just again showing that the model-based reconstruction using INRs just works so much better, especially at atomic resolution here. But what I want to do is just show you this example with the missing wedge and the small missing wedge, just to show you how effective the in-painting is. So we're working on extending these methods to atomic resolution. However, one thing that we ran into was that our current INR geometry, it was pretty good at low resolution, low magnification, but atomic resolution, it wasn't able to recover the high spatial frequencies as accurately, and it's pretty slow. So a normal INR in our current code, if you were able to do the classic reconstruction in a minute on one GPU, even with 16 GPUs, it still takes 30 minutes. So we're looking at different architectures. And the winner appears to be tensor decomposition, especially the K-planes, essentially factoring of your tensor train decomposition. And we're still working on the publication for this, but the code is available online. It seems like this architecture is much, much more effective applied to atomic resolution data. So here we're able to get the reconstruction time down to 5 minutes on a single GPU, but we're able to get all the atomic details. And not just that, but get the details a lot higher signal to noise than the conventional algorithm here. Okay, so the last section of my talk, I want to show you applying machine learning to ptychography. So ptychographic reconstruction is about the most complicated computational imaging method that we use in electron microscopy. And so we, of course, wanted to see if these machine learning techniques could be used to improve it. So the framework is exactly the same as I showed you previously. The only difference is instead of using an implicit neural representation, here we tend to use this UNet, deep image prior or deep generative prior here, but otherwise it's the same architecture. So why do you want to do this? Well, first I mentioned you can't pass in random noise. And the reason is if you do that, you get a very ill-conditioned output object and probe. And so this works in the literature for visible light processing for these deep image priors. It did not work for us. So instead what we do is we just run the normal pre-training loop using gradient descent. That gives us a guess for the probe and a guess for the object. And then we feed that into our deep generative prior and then use the weights of the deep prior to update the probe and the object to fine tune it and get a better reconstruction. And so this is the only modification that we've really had to make to the sort of literature deep image prior methods. One note on technical detail. This is multi-slice ptychography. So in the UNet, we simply use the channel dimension as our multi-slice or propagation direction along the beam direction. So that's how our code works in practice. Okay, so if you do gradient descent on gold nanoparticles on carbon, this is what one of our reconstructions looks like. And we deliberately used low probe overlap to slow down the convergence, right? And so even after 5,000 iterations, you can barely make out the gold nanoparticle above the carbon support. So exactly the same algorithm, but you put it into PyTorch and you use the atom optimizer, this is what you get. And so this figure really shows why me and many other people are such big fans of the atom optimizer. And it gives you the best of both worlds for first order and second order methods. So it's still got the stability and simplicity of a first order gradient descent method, but by adding momentum, especially adaptive momentum, you can very much speed up convergence here. And so it's effectively converged by 500 iterations. You can just see it's so much easier to see the particle when you have low spatial frequencies reconstructed here. So this you get for free. If you take your favorite gradient descent algorithm and just implement it in PyTorch using Atom Optimizer, this is what you'll get. But it still doesn't hold a candle to the deep image prior. It's pretty staggering here. So even with the Atom Optimizer, pixelated gradient descent, we still needed about 500 iterations to converge it. The deep image prior requires 10 iterations to converge it. And so what I'm showing here is 50 pre-train iterations plus 5 plus 10 and plus 20 deep image prior iterations. But the thing to be aware of here is that 50 is probably overkill. We could probably do 5 or 10 pre-training iterations, and that would be more than enough for it to converge here. And so I should quickly mention the deep priors here do take longer to compute per iteration, but nevertheless, it still changes it by more than an order of magnitude. And so this is a pretty ill-conditioned reconstruction, but we're able to get it to run instead of in 13 minutes, to get it to run in 1 minute and essentially fully converge. So that's the first reason to use this deep generative prior approach. Second is signal to noise. I already mentioned how good these architectures are for denoising. This is the great ptychography metal organic framework dataset that Gusong Li published with the Cornell group and his group in Nature Communications last year. Great test dataset. The upper right shows the raw diffraction patterns. They are so noisy. This is an extremely sparse experiment because the structures themselves are so susceptible to beam damage. So this is a standard pixelated reconstruction, and this is our deep image prior reconstruction. And for comparison here, the bottom, here's using just a deep image prior for the object, or just using it for the probe. But both of those results are worse than doing a deep prior for both the object and the probe. So I just want to zoom in and flip through all the different units, just cutting them out to show you the exquisite atomic details. Not only do you see the zinc atoms, the two brighter dots for stacked double zinc, and the two dimmer dots in the middle of each structural unit, but if you look at the lines connecting them, you can see these bulges that are essentially the benzene rings, the 6-member carbon rings that are showing up in basically every ring. And so here it's flexing a little bit because I'm scanning over the surface and cropping out different positions here at each one of the nodes on the metal organic framework here. And some of this distortion is because I rotated everything to be aligned vertically here. And there is some flexing in the structure too. Okay, so one last example of how great the machine learning reconstruction is. This is a data set from Kayla, now at University of Oregon, but it was taken, I think, when she was in Pinshane's group at Illinois. This is the twisted bilayer tungsten selenide data here. And so this is 2 layers of a 2D material stacked on top of each other. And when you do multi-slice electron ptychography, you can calculate that the resolution along the beam direction is going to be somewhere in the range of 1 to 4 nanometers. And for a standard sample, 20 nanometers thick, 2 to 3 nanometers is pretty typical. But for a 2D material like this, you want to be able to hit that lower limit, that 1 nanometer resolution along the beam direction. So in the upper right, I'm now showing slices in the vertical direction. Identical means when you fix all of the slices to be the same as each other, you have no depth resolution. However, if you then go to the third row in the upper right, pixelated, you can see we're able to separate the layers, but they're significantly smeared out and overlap each other in the vertical direction. The second line down, though, the DGP, that shows that even with no additional regularization, the network is able to learn that the two layers are completely separate from each other. And then if we apply a tiny bit of regularization, just positivity and a bit of softmax, I think, that gives you really, really nice sharp atoms in 3D here. So zooming in on the slices, so slice at 0, 3, 7, 10, 14, and 13 angstroms here, or sorry, 3 plus 10 angstrom slices, you can see we're able to completely isolate the two layers. And it's a little subtle. I'm not sure if you guys can see my mouse cursor here, but this lower left, for example, you can see individual vacancies of single selenium atoms that are missing from each of these individual layers here. And so in the lower right, now, what we're showing is plotting along the beam direction. And that Gaussian fit is about 1 nanometer or 10 angstroms, showing that we're able to hit the theoretical maximum spatial resolution along the beam direction. And one other experimental example that I can't resist showing, this is biological data from our paper a couple of years ago with Henning Stolberg at VPFL on bacteriophages. I think these are Phi92 bacteriophages. And this is just comparing the pixelated reconstruction in the left-hand column versus the machine learning reconstructions in the next 3 columns. And again, they are just so much better at boosting the signal to noise and recovering the low spatial frequencies, the slow to converge components of the reconstruction. So I do want to use this to highlight another sort of aspect of these. It's a lot less hyperparameters. It's a lot more robust. It's a lot more accurate, but you still have to make some architecture decisions. So for example, in our deep prior, how deep should it be? 2 layers, 3 layers, or 4 layers? Well, here in 2 layers, you speed it up a little bit. You can get it done in 100 iterations, but you're not getting that massive speed up that I showed you before. If you go to 4 layers, now the network converges shockingly fast, 7 iterations, but it only takes 6 minutes. However, there are a couple visual artifacts. So in the upper right, for example, that black spot, there's just a couple probe positions that have low enough numbers of electrons that the deep prior isn't able to auto differentiate the reconstructed field quite perfectly here. And so you find the best results, the best mix of time and quality, if you do 3 layers for the deep prior in this case. And so currently there is still some empirical determination of the best way to do the machine learning here. And so we are working on ways of automating this and giving sort of advice to users, or even directly predicting from the data sets how to do the best possible reconstructions. Okay, so I mentioned a tutorial for this one as well. Please feel free to copy down this tiny URL address. And so this is a deep learning ptychography DGP tutorial that has been placed in Google Colab as well. And this is using that metal organic framework data set too. And so it's a slightly, restricted binned version of it, cropped version of it, so that it would run in the tutorial window. But you can go through yourself and see how we do these pixelated and machine learning driven reconstructions. And I think there will be time at the end for me to quickly flip through these notebooks, but I also want to leave some time for questions here. Okay, so I will summarize my talk by saying everything that you're seeing there so far has been put into our QuantEM software package. And so this stands for Quantitative Electron Microscopy. This is meant to be a community effort for machine learning inverse codes and analysis codes for electron microscopy. And it is not meant to be limited to diffraction and 4D STEM. We're also doing spectroscopy. We're also doing 3D tomography and many different kinds of imaging in 2D and 3D. And so you can find it on GitHub on the electron microscopy org under QuantEM or QuantEM tutorials here. And more tutorials are being added every day. If you are interested in implicit neural representations, especially for 3D tomography, we have a paper on the archive. I cannot recommend learning INRs enough. It is such a useful tool for machine learning, and it's pretty easy to get started, especially if you do Gaussian splatting or one of the other sort of modern ways of doing these INRs. And then finally, if you're interested in the neural priors for electron ptychography, we also have a paper on the archive as well. And so you can follow up with the details there and go through and learn how we do the machine learning reconstructions of our data sets on the metal organic framework example in this tutorial that we use here. Okay, so before I jump into the notebooks, I do want to quickly acknowledge everybody who contributed to this work. I really want to thank Stanford for funding a lot of this work, plus Toyota Research Institute, the U.S. Department of Energy. They are continue to be patrons of our work, and Samsung in particular has contributed a lot to our metrology efforts. For the deep priors for electron ptychography, that work was led by Arthur in partnership with George and Steph. George and Steph are now at TU Delft and Berkeley Lab as PIs, respectively, and Arthur is still currently in my group here at Stanford. The electron tomography work was led by Cedric Lim, a PhD student in my group, in close collaboration with a NERSC scientist, Cornel Cassert, and on the experimental side, Saren Lee, a postdoc working for myself and Jen Dion. And then finally, the earlier work I showed you, the ptychographic atomic electron tomography, that was really driven by Philip Bells, who's now a professor in Germany, and many other collaborators are shown from Berkeley Lab in the lower right there. Okay, so thank you for your attention. I will very briefly now flip over to the notebooks and just quickly just show you sort of what's in the notebooks here. And so this is Google Colab. And if you want to, hide the top bar, have more screen, zoom in, I recommend tutorials on Colab when you don't want to install anything on your machine here. And so for this tutorial on the INR, you definitely want to flip your runtime over to being a at least T4 GPU, although it'd be better if you pay Google to use the A100. It'll be a lot faster here. And so this tutorial essentially downloads this ground truth phantom dataset that we use for testing. We do some basic reconstructions, and you can see the streaks caused by the CERT algorithm, the missing tilts, right? And then in the INR side here, we load the data set, set up our model using HSiren. HSiren is a periodic activation layer that we use to feed into our INR. And then we have wrapped the INR into this object INR class. And then all you have to do is give it the device, the model, and the shape. And then we usually add a logger for statistics, and then build our tomography INR from the model, and then set the parameters. So this is the learning rate. And so the learning rate for the tilts and the learning rate for the object do tend to be somewhat different from each other. And so these are some good starting values, but you might want to play around with it. Same thing for the scheduler. Cosine annealing will work fine, but there's lots of other options available. And then finally, for constraints, we don't do a little bit of smoothing and a little bit of positivity. That's usually enough to make it work okay. And then dot reconstruct. And so that's it. The optimizer parameters, the scheduler parameters, the constraints, the dataset constraints, all those come in as args. You specify the number of iterations, the batch size, you iteratively run it, and then you can see your total loss here. And then once you've converged it, you can then compare. So this is a comparison in the upper row of the machine learning reconstruction and the classic method in the lower row there. And so I'll skip the rest of this tutorial, but it's all available here if you're interested. Similarly, this metal organic framework ptychography, what we do is we load all the data. This is what a single diffraction pattern and a average diffraction pattern looks like. And then we calibrate the rotation using DPC, differential phase contrast, and we calibrate the convergence semi-angle. And this doesn't need to be perfect, just a good enough initial guess to pass into the codes. Then once we've done that, you can see the dark field and bright field, the incoherent imaging modes, you get nothing but noise. So these are virtual detectors here. However, even if you just run this optimum bright field or parallax or tilt corrected bright field or DPC, you already start to see the lattice. And so then what we do is we walk you through how to do the ptychographic reconstruction, iterative second, but single sideband non-iterative first. And here's a beautiful reconstructed phase. And then the Fourier transform shows the resolution's a bit restricted, but if you do proper ptychography, you can push out the resolution and get a better guess for the probe. And then finally here, this is using the deep image prior. It's exactly the same as the tomography. What you do is you just instantiate all these classes, in this case using a CNN 2D as our deep prior here, build the object model, build the probe model, and then that's enough to pass into this pre-train and then from models functions here. And then the pre-process just aligns all the experimental data. And then once that's done, specify the optimal, or sorry, the optimizer parameters and the scheduler parameters. In this case, learning rate's the same for all of them, and run it. And then this is a quick comparison, just showing the different iterations here. And here it is. This is what I was looking for. the Fourier transform of the pixelated and the deep image prior. And this is blowing up the intensity to show you the signal to noise is a lot better. And so it's not fully converged. This was smaller so that it would fit in Google Colab. But if you run this on your own machine, it's relatively straightforward to converge this. Okay, so I see that I only have about 5 minutes left here. So I'm going to flip back to this screen and be happy to take questions from the audience. And I see that there's 2 questions in the chat, so I'll probably try to answer those first here. So thank you all.
Good. Thank you.
Okay, question 1 in the chat. How about predicting the intensity values from missing wedge in 3D diffraction patterns? The answer is yes. So we are doing this already. So this is called diffraction tomography or 6D crystallography or 5D STEM or 4D STEM plus micro ED. It basically works exactly the same. However, I want to caution you, and I do have slides on this, but in the interest of time, I'm not going to pull them up. If you're learning diffraction patterns in 3D, you should be aware that you're still not learning the phase of each of those spots. So you can in-paint the missing intensity spots, make a prediction for it, but not the phase. And so that's why I think for learning 3D diffraction patterns, what you really want to do is you want to do it in combination with a phasing algorithm. So we are working on just such an algorithm where we combine INRs with the micro ED or 3D ED reconstructions here. And this last question, does that mean convolutional networks work well for electron diffractions? I would say yes, but when you have a lot of like sharp features, really high spatial frequencies, that's where the K-plane tensor decomposition tends to outperform MLP or CNN INRs. So more on that later. But I would say for imaging, convolutional networks are the state of the art. And for tomography or sharp diffraction spots or things like that, K-plane tensor train decomposition is the state of the art. But that's my opinion. You'll find lots of different opinions in the field here. Okay, Shantanu asks, currently MEP, multi-slice electron ptychography, is the most efficient method to reconstruct 3D information from a sample along a single orientation. However, papers record large dwell times, limiting its application to beam-sensitive materials. So I think that this is not really true anymore. So what he's asking is the current limitation the detector speed, or are there some other limits? I think the detector operating at 120,000 frames a second, the Dectris Arena, for example, is sufficient. You don't have enough electrons to run at full dose, even if you wanted to at that speed. A sort of standard electron dose at 120,000 frames a second will only give you 2,000 to 5,000 counts in the whole diffraction pattern. And so, for example, if it's beam-sensitive material, you drop it down to 10 to 100 electrons per angstrom squared. And if it's not a beam-sensitive material, you keep it at higher dose, like several thousand or tens of thousands of electrons per diffraction pattern. So the last bit here, the limitations towards fast MEP acquisition, I just don't think it exists anymore. So I think I can maybe quickly show you bear with me one moment, because I think this is a cool example to demo for you guys. So for example, when we're reconstructing something like a GAFET device, and we're doing, so meaning a transistor, right? Basically, you can do this type of data acquisition where we're able to record the full diffraction pattern for each one of these probe positions and then do a reconstruction in 3D here. This data set takes about 3 seconds to record currently, maybe as long as 10 seconds if you use a longer dwell time. The single sideband reconstruction, so the non-iterative ptychography, that takes somewhere in the ballpark of 10 milliseconds. And then the full iterative ptychographic reconstruction, usually in the ballpark right now of 1 to 5 minutes. And so that's kind of where we're at with this range of times here. I think it's all reconstruction algorithms now. That's the thing that's going to limit us. Okay, Austin asks, is the DGP trained on a per sample basis? Absolutely. It was pre-trained with the Atom Optimizer. I think that is true in all our cases. We use the Atom Optimizer for the pre-training and for the final training. Like the DGP beats the atom optimizer on gradient descent, but it itself uses the atom optimizer, right? So I think that they're somewhat different from each other. You could do gradient descent and then use atom on the second step, or use atom on the first step, or as we do, use atom on both here. So but the first part of this question, the deep priors pre-trained on a per sample basis, I should be very clear about this. I didn't emphasize it. This is talking about self-supervised machine learning with a new network trained for every data set, for every reconstruction. We have found that self-supervised machine learning absolutely destroys supervised machine learning in almost every application. And so we've switched from supervised ML in almost every project we do to these self-supervised new networks trained on every individual sample. Okay, Garrett, do you want me to answer the last two questions, or am I out of time?
Let's just answer the next two questions and then we thank you again, okay? So that's how if it's reasonably quick, I don't know, it seems to be quite straightforward, right?
Yeah, so Shantanu is asking, in the pixelated FFT in the notebook, there's 4 spots in high frequency zones. Are they an artifact? Yeah, it's probably a detector readout artifact. With a little bit of filtering, I'm sure we could remove it. That's definitely an artifact. And then returning to 3D electron diffraction, Arizo again asks, solving the problem for 3D electron diffraction patterns from Moss here, indexing the images. You're asking if a graph representation for the data set is suitable. Yes, if you're working in block wave space to solve the intensities that way. But if you're working from the 3D voxel cloud, no, right? I would use the INR to represent the intensity, to inpaint both the intensity and to inpaint the phase. But in order to inpaint the phase, you have to couple it with a phasing algorithm, right? And so you have to take what people are doing already. So use the existing like ShellX reconstruction, but instead of basically, I guess I could just flip back very quickly. So in this case right here, it's exactly like what you would imagine. You're using physics model is this ShellX forward model. The object is either your list of diffraction spots, HKLs, in which case you use a graph representation, or the pixel or voxel intensities, in which case you use the voxel representation. But the thing I would add into it is generate the phase and generate the intensity using an INR, some kind of deep prior, right? And so everything from the deep prior onwards here absolutely should probably just be ShellX or whatever physics model you would use for 3D electron diffraction. So that's my advice, but feel free to email me if you want more opinions on that. We want to try it too. We just haven't gotten to that one yet. Okay, yeah, thank you all for your attention. And I hope you're enjoying the summer school.
It was very nice, excellent. And I hope I prepared every one of you so that you could follow that on the diffraction side. Thank you so much, Colin. And so we move on to our next talk from Austin Houston. He is a graduate student about to be finished here. In between writing the thesis and other things he needs to do.